Hello again, learners! I am Sir Skip Pimentel, your Science 10 teacher. Welcome to our video lesson. You have learned from your previous lesson that the solid part of the Earth, the lithosphere, is divided into several pieces called plates. These plates are gradually moving to form different geologic features such as mountain ranges, volcanoes, rift valleys, and ocean ridges. These events also explain why we experience earthquakes. What causes these plates to move? What is the evidence that the Earth's plates are moving? If there were movements of the plates, do you think the position of the continents of the world in ancient times is the same as we see it today? Before we continue, let us first test what you know by answering your pre-assessment questions. Just a reminder, make sure in your pre-assessment we are honest in answering the questions because this is the key to our learning. In this video lesson, we will discuss some of the well-known theories developed from a time when there were no modern tools or instruments to support this up to the present time where modern technologies are already available to reveal the evidences of plate movements. In our previous lesson, we already have learned that the Earth we live in is composed of different layers. Although scientists did not go and dig directly into the deepest part of the Earth, the knowledge of what is inside the Earth comes from their observation through seismic activities. We have also learned that earthquakes, volcanoes, and mountain ranges were formed because of the movements of the oceanic and continental crust. This idea of moving plates started when a German polar researcher, geophysicist, and meteorologist named Alfred Wegener noticed something on the map. Many of you might have already seen it. Did you notice something? It seems that these continents almost look like puzzle pieces. Look again. Especially when you look closely at the shape of the eastern coast of South America and west coast of Africa. Do we have the same thing in mind? It seems like they fit together. This strange shape phenomenon prompted Alfred Wegener in 1912 to introduce the continental drift theory. This theory suggests that the continents were actually once connected and somehow ripped apart where they are today. Wegener didn't just think that the continents are moving. He actually believes that all the continents were once connected and they have just drifted apart to their current locations. He even came up with the name to that supercontinent that existed in the past. He called it the Pangaea, which means all Earth. This is evidence number one, called the geological or the continental fit. But would feeding edges of the continent be enough proof that the continents are drifting? For Wegener, it is not enough. So he went to the library and dug piles of books to gather more evidence to support this theory. He has come up to evidence number two, the fossil evidence. While he is researching in the library, he becomes interested to fossils. particularly that of a fossil of the Mesosaurus, an ancient reptile that only lives in shallow and fresh water. What Wegener discovered is that there are only two places where we could find fossils of this fresh water creature. That is in the eastern coast of South America and west coast of Africa. Now, some others might say, there are possible explanations to this. Maybe some of them learned somehow to fly across the Atlantic Ocean to inhabit the other side of the continent. Well, there is no evidence that they have developed wings. Some may say that maybe they have swam across the ocean, but it is also not possible because the distance is too great and they cannot survive in salt water. Wegener said, while the Mesosaurus roamed freely, walking across the land masses, South America and Africa were connected. And when they become extinct, the land masses were torn apart and separated, carrying some of the fossils to what will become South America and some to what will become Africa. What's amazing about this is that he discovered that there were other organisms that live in the past that have similar fossil distribution. One example is the Cynonatus, a mammal-like reptile roaming the terrains during 250 to 240 million years ago. Its fossils are found only in South Africa and South America. As a dominant land species, the Cynonatus would not have been capable of migrating across the Atlantic. Another one is the Leistosaurus. Fossils are only found in Antarctica, India, and South Africa. Similar to the land-dwelling Cynonatus, the Leistosaurus would not have the swimming capability to traverse any ocean. And last, and possibly the most important fossil evidence, is the Glossopteris, found in Australia, Antarctica, India, South Africa, and South America, all the southern continents. Known to have large and bulky seeds, possibly could not have drifted or flown across the oceans to a separate continent. This suggests that the continents must have been joined at least one point in time in order to maintain the Glossopteris' wide range across the southern continents. These fossils show very unique distribution patterns that suggest that the continents were once together. In fact, if we reassemble the continents and map out the distribution of these fossils, they match perfectly. But Wegener knew he needs a stronger evidence. So he went back to the library and been fascinated with rocks and other geologic features like mountain ranges of the past. He found an interesting pattern. At the northern part of the Atlantic, he noticed that the mountains in the northeastern US and the mountains in the northern Europe match perfectly. They have the same type and age of rocks. Some of the examples are the Appalachian Mountains of eastern North America, linked with the Scottish Highlands. Another is the familiar rock strata of the Karoo system of South Africa, matched correctly with the Santa Catarina system in Brazil. And the last one, Brazil and Ghana mountain ranges agreeing over the Atlantic Ocean. This found evidence suggests that these mountains were once connected, and as the continents moved, they separated. This is evidence number 3, rock and mountainous terrains. Again, Wegener returned to the library and this time returned to his roots as a meteorologist. He looks on evidence on warm and cold weather in different parts of the world. Guess what? He found something fascinating. He first looked at the glaciers, giant river of ice that moves slowly across the Earth's surface. Of course, glaciers are supposed to be found on cold parts of the Earth, on mountain tops, at the North, and at the South Poles. Now, something interesting about glaciers is that when they move over the rock, they leave evidence in the form of scratches or cut into the bedrock. We call this glacial striation. Now, how this relate to the continental drift? Now, let's go back to our present-day map, particularly in the tropical rainforests of South America and Africa. In the bedrock of these continents, you won't believe, lies an evidence of glacial striation. Now, some of you may ask, how can there be evidence of glacial striation in tropical rainforests? Unless it was not always a tropical rainforest. What does that mean? This suggests that these regions were not always warm and near the equator like they are now. They were once down near the South Pole where could have been cold enough to have glaciers, and after a very long time, move upwards. This is evidence number 4, glacial striation. Wegener's search for evidence did not end here. He began to explore a little deeper. He came across this rock called bituminous coal, the one that we burn for energy, a fossil fuel made from compacted plant remains, meaning these rocks came from dead tropical plants in the forest ground, getting compressed for millions of years to form coal. You will be surprised. Here are the locations where coal deposits were found around the world. Did you notice something? Most of the coal deposits found are located on cold regions, where least you expect to have tropical plants to survive. But yet, there are coal deposits on Antarctica, Northern Europe, Northern Asia, southern tip of Africa, northern part of the United States. These are not tropical regions. Now, you may ask, how can there be coal deposits in these cold regions? This suggests, like that of the glaciers, that once these regions were tropical and that the continents have moved downwards over time. This is evidence number 5, coal deposits. To further understand the idea of Alfred Wegener and the evidence of continental drift theory, let us perform activity number 1, entitled A Journey from the Past to the Future. We're going to find out what are the evidences of the continental drift theory. Here are the materials you will use. The first one, a photocopy of the 7 continents, a blank globe map, pair of scissors, and a world map. Despite Wegener's gathered evidence supporting his idea about drifting continents, during his time, the scientific community rejected him for some problems. The first one, his estimate about the speed of continental motion is 250 centimeters per year was unbelievably high. And the last one, he cannot explain what causes the continents to move.
Nevertheless, Alfred Wegener didn't give up and continued his expedition to search for more evidence, but later on died on 1930. It took about more than 50 years before his theory of continental drift was accepted in the 1960s.
Let us see if you have understood the essence of the first enrichment activity. You may now answer assessment number 1. Despite Wegener's death, his sacrifice and contribution were not ignored. As I said earlier, after many decades, his theory was later accepted and continued by scientists of later times. In 1950s and 1960s, new techniques and modern gadgets were already available. The sonar, a sounding gear developed in the 1930s, was used to bounce sound waves off the seafloor to determine its depth and features. With the use of sonars and submersibles, scientists had a clearer view of the ocean floors. They have discovered underwater features deep within the ocean.
Harry Hammond Hess, a geologist from Princeton University who was in command of one attack transport ship, the USS Cape Johnson, discovered that the bottom of the sea was not as smooth as expected, but full of canyons, trenches, and volcanic sea mountains.
They have also found a system of ridges or mountains in the seafloor similar to those found in the continents. These are called mid-ocean ridges. One of these is the famous Mid-Atlantic Ridge, an undersea mountain chain in the Atlantic Ocean. In the early 1960s, scientist Harry Hess suggested an explanation to the continental drift. This is the seafloor spreading. According to this theory, hot, less dense material from below the Earth's crust rises towards the surface at the mid-ocean ridge. These materials flow sideways, carrying the seafloor away from the ridge and creates a crack in the crust. The magma flows out of the crack, cools down, and becomes the new seafloor. Over time, the new oceanic crust pushed the old oceanic crust far from the ridge and allowed the creation of new bodies of water. In the place where two oceanic plates collide, or where an oceanic plate and a continental plate collide, a subduction zone occurs. As the new seafloor is formed at the mid-ocean ridge, the old seafloor farthest from the ridge is destroyed at the subduction zone. Harry has observed that the rate of formation of new seafloor of the mid-ocean ridge is not always as fast as the destruction of the old seafloor at the subduction zone. This explains why the Pacific Ocean is getting smaller and why the Atlantic Ocean is getting wider. If the subduction zone is faster than the seafloor spreading, the ocean shrinks. When the seafloor spreading is greater than the subduction, then the ocean gets wider. To understand further what Harry Hess and his men discover, we are going to perform the next activity. Activity number 2, entitled Where It All Begins. We are going to find out what is seafloor spreading. Here are the materials you will use. Number 1, ages of oceanic lithosphere map. Second, the diagram of the Mid-Atlantic Ridge and the oceanic crust. Here are the procedures and guide questions. This time, geophysicists have found out something about magnetic rocks in the seafloor that somehow provides a particular pattern which proves the movement of the plates. Like we already know, our Earth has a north and a south pole, both geographic and magnetic. Geographically speaking, north is always north and south is always south. Magnetically, however, the north and south pole flip irregularly every few million years. This phenomenon is called magnetic reversal. But before we explain this further, let's recall and watch this video about magnets. A magnetic compass is a tiny magnet, with its needle or pointer acts as north. It points to the geographic north pole of the Earth, where actually at present, it is now our magnetic south pole. Now, maybe some of you are confused. Di ba north yung itaas at south yung ibaba? Geographically, yes, but magnetically, it is not. Remember, a compass needle, which serves as the North Pole, will only be attracted or pointing to the opposite magnetic south pole of another magnet. In this case, our Earth's magnetic south pole. The magnetic reversal, also called the magnetic flip of the Earth, happens when the North Pole is transformed into the South Pole, and the South Pole becomes the North Pole. Now, why did this happen? Scientists believe that this happened probably because of the changing direction of the flow of materials in the Earth's liquid outer core. What is the evidence of magnetic reversals?
Further evidence came along by 1963 as geophysicists realized that Earth's magnetic field had reversed polarity many times, with each reversal lasting less than 200,000 years. They have found out that history record these flips or reversals in minerals or rocks that acted as a compass, frozen in time when that part of the crust is formed.
What is the importance of this discovery? The discovery of the magnetic rocks near the ridge following a pattern strengthened the seafloor spreading theory. These magnetic patterns allow our scientists to understand how old the materials are on the seafloor and how fast its movement from the mid-ocean ridge. Over the last 10 million years, there had been an average of 4 to 5 reversals per million years. As new rocks are formed to the ocean floor from the ridge, and approximately equal amounts on both sides of the oceanic ridge are also added. Surveys of either side of the mid-Atlantic ridge show a symmetrical pattern of alternating polarity stripes. To understand further how Earth's magnetic reversal strengthens the seafloor spreading theory, explore the last activity to understand what happens deep under the ocean at the mid-Atlantic ridge. Our activity number 3, the enigmatic magnetic reversal. In this activity, we're going to find out what is magnetic reversal. Here are the materials. Diagram of the Earth's magnetic polarity. Here are the procedures and guide questions. Now let's find out what you have learned from our lesson on seafloor spreading and magnetic reversal. Please answer the following questions. Most of the changes on the Earth's surface take place so slowly that they are not immediately noticeable by humans. The idea that the Earth's land masses have broken apart, rejoined, and moved to other parts of the world forms part of the plate tectonic theory, which you will be exploring in the next module. Since there are strong evidence that continents are drifting as supported by the continental drift theory, seafloor spreading, and magnetic reversal, can you predict the next movement and locations of the continents 100 million years from now? Is there a possibility that another supercontinent might be formed? Let's find out in this next activity. Our activity is Pangea Ultima, the last supercontinent. We're going to find out how does climate change related to the movement of continents. Here are the materials. Coloring materials, it can be pencil or crayons, short bond paper, and a world map showing the present location of the continents and their movements. Here are the procedures and guide questions. Great job for finishing this module on evidence of plate movements. You are now ready to move toward to the next module. But before that, let's evaluate what you have learned so far from our lessons. That ends our lesson for today. I hope you have learned a lot from what we have discussed. As I say goodbye, before the end of this video lesson, let us enjoy listening and dancing to the music we have prepared for you. May this song remind us all of the contributions made by Alfred Wegener and Hammond Hess. Bye!
Alfred Wegener was his name. A continental drift, he explained. A fossils match up, climate is changed. Landforms, they fit that way. Called it Pangea, which means all lands. Scientists don't give him love. Come on, come on, come on. Reaching out to prove with evidence. No matter where they go, he knows the plates once closed. Alfred Wegener was his name. Continental drift. Now Wilson's theory includes it all. Driven, plate tectonics motion, subduction formation. Alfred Wagner was his name. A continental drift, he explained. Fossils match up, climate has changed. Landforms they fit, land